We're gonna forge on. We've actually taken this session that you guys are getting today was originally conceived as a full day, 8.5-hour session. So you're getting a compressed version of that today. So I'm going to keep going and forging ahead, and we'll get through a bit more of that. I did want to, before I start, I did want to introduce myself a little bit farther. My name is Mark Rosen. My role with Building Knowledge Canada is as the Director of Building Science, but I was an energy advisor carrying a blower door fan on site for about 10 years. I've blower door tested about 3,000 new homes. And I was born and raised here in Alberta, spent about 23 years of my life in Ottawa working in that climate zone, and recently have moved to BC and have been gaining the BC perspective. So from that stance, I'm okay with whichever province you want to poke fun at today. I'm game for all of them. And they all have very different problems and practices. So because I've been gone from Alberta for 27 years now, I'd just like to know a bit more about your practices here that'll help me contextualize this part of the presentation. The first question I want to ask is, when we had the Slido polls at the beginning and you were answering questions about using high performance windows, has your understanding of what a high performance window potentially changed based on what Darrell presented to us today? Some hands there. Yeah, I think, everyone may have come in with a bit of a different perspective on what a high performance window means to them and to their projects. How many of you are regularly using triple glazed windows in your homes today? A handful of you are doing that. And double glazed, high performance double glazed? Some there, okay. How many of you are, as a default or as a standard, installing either air source heat pumps or air conditioning in your homes today? Some? Are you finding more requests, or that it's becoming more common that we consider cooling? Whereas I think, growing up in Alberta, none of my neighbors had air conditioning. It was not on the radar, but I think fair to say we're seeing a bit more requests for that. Last question, how many of you are getting requests for more and bigger windows in your houses? Building homes with more windows than you used to? Some? Okay. Thank you, that's very helpful. So, my role coming to you today with the energy advisor and building science perspective is to walk you through some of our process as we help to optimize window selection in support of the builders that we work with. And as we do this, I'm going to talk about some tools, same as kind of the discussion of window coatings and which plane they go on. Some tools that it'll be useful for you to know about, but don't worry too much if I sort of breeze through them and you don't have a full grasp of them. You can ask your energy advisor for more help in a lot of the stuff that I'm going to talk about today. But what we're going to take you through is a bit of an Archetype home case study. Now, I'll apologize in advance. In the spirit of poking fun at the provinces, the case study is from Toronto because Toronto is the center of the universe and that's where all the case studies get developed. But the lessons that we can pull from this case study are still relevant, even though we're in a very different climate zone here. In fact, a lot of the observations from the case study are going to be exaggerated because we're in a colder and sunnier climate here in Red Deer and Edmonton area. So we're going to look at a case study Archetype home. We're going to look at the implications of window selection on energy performance. We're going to look at how it impacts your mechanical systems and your design of sizing of heating and cooling for the systems. We're going to get into a little bit of carbon or carbon emissions. And we had the question at the beginning of the day about embodied carbon. I'm going to dive a little bit with some definitions into operational carbon emissions and embodied carbon emissions, because these are coming in future versions of codes and we have to start educating ourselves about what they are. And then we will talk about comfort as well, which I think at the end of the day is what our goal to our clients, to our home buyers, is to deliver comfort. And Windows is a really big piece of that comfort challenge or that comfort puzzle. So there are several modeling tools that as energy advisors we use on a daily basis to help our builders navigate compliance with codes, compliance with voluntary standards, and to deliver on these promises of comfort. The one that you'll probably hear talked about the most is called HOT 2000. How many of you have heard of HOT 2000 before? Great. So HOT 2000 is managed and developed by the Government of Canada. It is sort of the default energy modeling tool for residential work across all of Canada. So it gives us a very level playing field and the ability to compare results from different provinces one to the other, which helps us as we develop that. There's a tool floating around out there that in LEEP sessions like this you might hear talked about called CBAT. CBAT stands for Cost Benefit Analysis Tool. It's another tool that was developed by Natural Resources Canada. And what CBAT allows us to do is to take the energy outputs from HOT 2000 and costing data that has been researched across industry and bring them together in a tool that helps you select energy optimized packages for cost. So it'll actually take 80,000 plus runs, 80,000 energy models with different configurations. This one with R20 in the wall, R22, R24, 1 inch of exterior, 1.5 inch of exterior, etc. Airtightness levels. Run all of those and help you identify a very cost-effective package based on your targets, based on your goals. So we're going to look at that a little bit. There are some other tools around HVAC sizing that are becoming available that energy advisors are getting training on, and that's because we are really starting to understand that right sizing of mechanical equipment is not only important for the operation of the equipment itself and for the comfort of the homeowners, but is dramatically influenced by the window selections that we make. And finally, we're going to talk a little bit about a tool called MCE2, which is the Material Carbon Estimator tool. And this is a tool that helps us to look at the carbon impact of our decisions, both in the materials that we select and in the energy that's used by our buildings as they operate in the real world over time. So I'll introduce you to the Archetype home. This is the model for which all the numbers that we're going to see was used. As we see the numbers, keep in mind that because we're talking about a specific home, numbers for your homes will be different, right? This is just a case study home, and I already mentioned it's in a warmer climate zone, so it'll be a little bit different from that perspective as well. But it's a fairly standard house design, a new house design, about 2,700 square feet on 2 stories, relatively small but numerous window openings. The window to wall ratio for this home is about 20%. Has an inset garage, and an unfinished basement. So a fairly common housing archetype, at least for the GTA. Does this look like a familiar house plan to you? Do you build very different houses here? How many would say houses are bigger here than 2,700 square feet? Smaller? We're about in the range? 22, 23? Okay, so it's maybe a little bit of a bigger home example than that. Okay. These were the reference house minimum specifications for this home. This is for zone 5. We're in zone 7A here, so some of these are slightly higher here. A reference house is the baseline. So you're going to hear me use the term reference house, and you're going to use the term proposed house. Reference house is the minimum code, and it's the performance of the reference house that we're going to measure all of our improvements against in the proposed house. The proposed house will be, in this example, the house that we intend to build, the house that we're trying to make the decisions about. So I'll highlight here that on the reference house, the code assumes in its base case a window value of 1.84 U, an energy rating of 21, and a fairly low solar heat gain coefficient. So based on what we've learned from Darrell this morning, this is quite a high U value, right? Not a great thermal window, but it's quite a low solar heat gain coefficient. This is on the lower end of that ratio. What this does is, in a heating climate like Edmonton or Red Deer, this actually means that the reference house requires more energy to meet the heating needs because it's not getting free heat from the sun. This helps when you're trying to demonstrate energy compliance better than code. That decision will help us typically. However, Darrell mentioned cooling loads, and we're going to look at these later. This also means that the reference house is going to have a fairly low cooling load, and that any decisions we make that use a higher U-value window may mean that our proposed house ends up with a higher cooling load, a higher peak cooling demand than the reference case it's being compared against. As I mentioned, this house is about 20% fenestration door-to-wall ratio, so that would be probably on the higher end, maybe not full custom numbers that we see. We see custom homes in my markets that I work in, regularly exceeding 22%, 25%, even up to 30%, because custom home buyers like to customize that and go with much, much bigger windows. But I think this is on the high end of typical for tract type model homes. The mechanical system for the reference house uses a standard gas furnace, air conditioner, a 14.5 SEER air conditioner, standard gas hot water tank, and no drain recovery, no heat recovery ventilator either. So quite a base package, a typical code base package. So the first thing we're going to look at, and we've already started to dip our toes in here, is what is the impact of orientation and glass to wall ratio on the energy performance of your house. Starting with the house, if we just take that reference house and we spin it, and we try modeling it in all 4 cardinal orientations, we're going to see how much the needle moves on the total number of gigajoules that we consume. Gigajoules is the number that we use to talk about absolute energy instead of talking about an abstract scale of nothing or talking about meters cubed of gas or kilowatt hours of electricity. Gigajoules is our metric as energy advisors to tell you about energy efficiency. Lower is better, right? It's an actual number of energy gigajoules used. So just spinning the house, we can see that the numbers do change. And in fact, if we optimized this house, if we had no restrictions, building this house with the front facing north would use the least energy because the other orientations are consuming slightly more energy due to less free energy from the sun. But I will point out that with this archetype, they're not very big changes. Orientation for this house, I'm going to say, doesn't really matter that much. Imagine for a moment a townhouse, a middle unit townhouse, where 80% of the windows are on the back face of that townhouse. And how do you think these numbers might look if we were looking at that example? It might be very different, right? So when you have a house with reasonable distribution of windows on all 4 sides, how you spin that house doesn't really necessarily move the energy needle too much. But if your windows are heavily biased to one side of a house, that's something you might have to pay a little bit more attention to. Conversely, if we look at, in this table, we've got across the top ratios of window to wall in different percentages, and on the side we've got the 4 cardinal orientations. We see that increasing or decreasing the ratio of windows to wall has a much bigger impact on the energy number than spinning this house. Right? Going up to 23% actually adds almost 3 gigajoules of energy alone, and going down by 4% can save 4 gigajoules of energy, or 2 or 3% of the energy, which has a much bigger overall impact than the orientation and the way that it is facing. It's a very small difference. So the conclusion here is that in this archetype, window area has a much bigger impact than window orientation. In colder climates, like this one, 7A, with more sun, then that impact will be exaggerated, right? You're going to get even more free heat with a larger area, but you're also going to lose a lot more heat because you're in a colder climate zone. And if you don't have a good U value, that heat loss may even outweigh what you gain in solar heat gain. Bit of a touchy remote. Let's see. Okay, so just to break that number down a little bit, that 114 gigajoule number in this example is the total energy used by the house. About 26 gigajoules of that is the people living in the house and the TVs that they plug in and the lights that they use and their appliances. But still you see that 64 of the 114 gigajoules is heating energy. Well, only 5% of that is cooling energy. So even though we're going to talk about heating and cooling loads in the same breath today, we have to keep in mind that we are still a heating dominant climate here, right? We're designing for the winter condition first and foremost. Summer has to play into it, but it's secondary in a lot of ways. So in the process of optimizing this home, in an integrated design process that you might go through with your energy advisor and your trades, this would be the point where we might use a tool like CBAT to try and find a good starting point. And what this would allow us to do is take the energy base model that we've got, put it into HOT 2000, run it through a simulation that does 80,000 different combinations of it, and then say, okay, we need to meet 20% better than the building code, for example, and we have this window to wall ratio, and we're not going to use any PV, and we want to know what package we're going to get to start there. So this is just an overview of the process. I won't spend much time here on what the tool does, but it allows you to choose what house you're going to use, choose a base case to compare it against, identify your energy efficiency target, identify which measures you want to consider. So you could eliminate, for example, maybe you don't want to consider any windows that are worse than 1.6. So you just leave that off the table. And then you can review and adjust your costing data before you generate your optimal solution. And this is an example of that output. So we've asked the CBAT tool in this case to give us a package, a specification package to meet Tier 2 of the National Building Code, Tier 3 of the National Building Code, and Tier 4 of the National Building Code. And we've asked it to prioritize for capital costs to the builder. You can also have this tool optimized for overall costs to the homeowner, which might look a little bit different because that might prioritize things that save on the operational cost of energy versus things that are less expensive to put into the house in the first place. What I'll draw your attention to on this slide is that as you move up to higher energy performance tiers in the National Code, what the optimization software tends to do is recommend better windows before it recommends increased amounts of wall insulation. And this is going back to the point that Darrell made, where if we know that an average wall is an effective R16, but a double glazed window in the middle of that wall is only an R2, then we've got an easy starting point for how to improve the overall average of that wall. The other thing with this CBAT package, I'm just skip through these, is that this is only a starting point. Right? Your energy advisor would then take this package back into an energy model and start to tweak it and make sure that it really represents your supplier's availability of products and your costs and your preferences as well. For the energy advisors in the room, there are also advances in tools coming out for HOT 2000. One that we're really excited about is Volta Snap, which gives you a new interface for interacting with the software and new reporting abilities, which as builders, if you've ever gotten a HOT 2000 report and tried to read it, you know sometimes they can be a little bit dense. It can be hard to find the information that you need. This tool is helping navigate that. And this tool is also giving us as energy advisors the ability to run those 80,000 models in the background ourselves, as opposed to having to ask the technical authorities at NRCan to do it for us. So, bit of a teaser there. An example of one of the outputs from Volta. I won't spend a lot of time on this today, but it gives you the ability to run multiple scenarios. So you might take this package that was generated by CBAT and then tweak it with a bunch of different scenarios to understand the impact of each of those runs. A bit more detail there. I'm going to move on so we can get to the meat of the stuff today. Okay, this is an output of what the back end of that looks like. And this is scary and intimidating, and I don't think you ever will see this again in your day-to-day operations. But it's a little bit of a peek behind the curtain as to what goes on. So when I mentioned the 80,000 plus runs that the CBAT tool uses, this is effectively a visual representation of those runs. And every single point in this point cloud represents a very specific combination of measures or specification package, and the balance of cost on the y-axis of that package versus energy savings relative, in this case, to the Ontario Building Code along the x-axis here. And so all of the bottom points on this cloud represent the most cost-effective package that can be achieved at that given amount of energy savings relative to OBC. So if we wanted to look here at 20% and lowest cost, we'd be clicking on one of these points. And that's effectively what the CBAT tool is doing for us. It's selecting that point and giving it to us. What the CBAT tool doesn't do is give you the next best point or the third point above that. And so what it suggests as the most cost optimized package might not be your most cost optimized package, because you might have a dealer agreement on, let's say, a certain product that gets you 20% lower than cost on that. Go ahead.
What sort of information would you need from the builder in order for you to run this?
Right. So to really dive into this, if you have a builder who thinks that this is going to be a useful tool to work with long term, in one of the Excel tabs in the CBAT tool, you can actually customize all of the cost inputs directly. Now, costing information is one of the most closely guarded secrets, I think, that most of us hold in the construction industry. But if you're working with your energy advisor and there's a level of confidentiality there, you can actually make those your costs, and this will be much, much more relevant as a result. But really, the only other inputs that are required are anything you need to build a HOT 2000 model in the first place, and any non-starter measures that you don't want to consider in this at all. So maybe 0.7 windows you value are not available, so you're just going to take that right out. or 0.6 air changes is not achievable. You just take that right out. Okay, so a lot of technical stuff that's possible in the back end. As I said, each one of these points has all of the specifications attached to it for that package. But the end result is we're going to end up at a starting point where we're going to be evaluating the impact of the windows we choose on the package that we're now building to get a certain amount beyond code. And that's where we're going to spend most of our time today. So here's some familiar terms that you're all becoming experts on now. We've got U value for 3 different windows across the top of this chart. And for each U value, we're looking at 2 different solar heat gain coefficients, a 0.4 window and a 0.19. So this would be considered a low solar heat gain window. A 0.4 would be considered a mid solar heat gain window, a very common one. We're not in danger territory of high with either of these examples. In this archetype home with the 20% window to wall ratio, what we see is that as you stick within one U value, high solar gain windows will use less energy overall than low solar heat gain windows. And we think, great, let's go with the 0.4. We're going to use less energy. It's going to be easier to comply with the code. We're done. Well, caution. That's what we're diving into today, right? That 0.4 might not take into consideration that the biggest window in the house faces due west in the living room. And in July is absolutely going to cook people that are trying to watch their family movie night or the hockey game at 7 p.m. when that sun is cooking them, right? So, okay, we're going to try and optimize for comfort. Well, now we're going to move to a solar heat gain window that has a lower value, and we're going to see that we've addressed the comfort issue, but now the energy consumption has gone back up. So we have to realize that we've got 2 levers here that we can pull. And as we go down in U value with the low solar heat gain coefficient, we can start to achieve the same sort of performance that we started at. So if this was good for our scenario, and actually I think these happen to match exactly the 35 ER window label that we just looked at, you dive down here and realize that a 1.22 and a 0.19 is achieving the same end result. Might have a lower ER value on the label, but was going to lose less heat in the winter and gain less heat in the summer, which makes for a more consistent interior environment. Some would say, I might even be so bold as to suggest that that's a more desirable condition, right? So don't fixate only on the energy number when you're looking at your windows. You have to consider occupant comfort in the same breath, otherwise you potentially are going to run into warranty and consumer complaints at the end of the day. There is a tool online for allow you, if you were working, oh sorry, Darrell, please jump in.
If you go back to that last slide, what I find interesting here, and I experienced this in my own house, is that in the summertime, because of the low solar heat gain, I don't need air conditioning. In fact, my wife is always telling me in the summertime, turn the heat up, because there's not enough heat from the sun to warm the house up from what it was overnight. So you will find that this one number, you're going to spend more money on the 1.22 windows, but at the end of the day, it might save you on putting air conditioning into that building. Right. So don't just think in terms of windows, think in terms of the whole system.
Yes.
Can I ask the builders in the room a question? What sells a home, comfort or energy efficiency? Comfort? And I only ask because this isn't a really important point when we're talking about the different values. And to Mark's point here, we can get to both. We can get to an energy efficient combination. We can also make it comfortable and know that our consumers actually want that product and that we're going to get value out of that product that is tangible to them.
Yeah. And you've inadvertently touched on one of my favorite topics, which is the psychology of home buyers, right? What do they want? If you look at the surveys of what people think they wanted when they bought their house, they will tell you energy efficient measures matter to them. But very few people will ask about energy efficiency when they walk through the door of the sales center. It's not what drives people to shop for homes. And I'm going to go on a small tangent. I'm going to allow myself a few minutes on this, but comfort is something that's very attractive to people. But how many people do you think buying a new home expect poor comfort? Comfort is a default assumption, right? And if you use comfort ambiguously in your sales pitch, then the conversation goes something like this. Well, we're going to build you the most comfortable home. Well, it's a new home. Aren't they all comfortable? Well, ours is more comfortable. Well, how much more comfortable? Well, much more comfortable. How do you quantify more comfort? Because what is your competitor saying down the road? Theirs is also more comfortable. That's hard to differentiate. But if in that moment you can say, we use a window with a lower U value so that when you're sitting next to it in December in the dark, you don't lose as much body heat to it. That's going to make you more comfortable. Then you're starting to impress them with how well you know your product and with something that actually might differentiate you from your competitor, right? So you have to think in terms of comfort, and you have to think in terms of energy efficiency, and then you have to also think in terms of how do we communicate this to people who don't think they have to worry about it, so we can add value. And that's a whole separate seminar. Maybe we can come back for that one. But thank you for the questions. So in some cases, you need to find windows that are compliant with Energy Star if you're building an Energy Star compliant home, or it's a requirement of a bylaw or development standard. There is a tool on NRCan's website to search for Energy Star compliant windows, but your suppliers will also help you with this. If you tell them you need an Energy Star compliant window, they will tell you what product they've got available that meets that criteria. So the next example that we get to look at here is for an example home. We mentioned that sometimes it makes more sense to upgrade your window instead of adding more insulation to the wall. And we actually modeled this to prove that this was the case, which was really kind of cool. So on this chart, you've got energy savings on the left-hand side. So the chart is showing the percentage of energy savings. And then it's showing different measures that we did to the home along the bottom axis to show what the relative energy savings were on this home. And improving the windows to a 1.44 low solar gain of 0.26 window saved 7% overall energy. Going to a 1.2 went to 10% energy savings. And if you look at the comparables, adding an entire R5 continuous insulation layer to the house, so 1 inch wrap for the whole house, only saved 2%. Adding 2 inches to the whole house only saved 5%. So in fact, improving the windows moved the needle farther in this case. But there's a key takeaway here. It's because this house has 20% fenestration door-to-wall ratio. If you're at 8% fenestration door-to-wall ratio, then those might change, and quite dramatically. So we put it in a different type of chart to have a look at this. So this chart kind of highlights the sweet spot. At the red line, you have the point on the fenestration and doors-to-wall ratio at about 17%, where it starts to make more sense to move from a double glazed window at 1.6 to a triple glazed window at 1.2 than it does to put 2 inches of continuous insulation on your house. That's the crossover point. So everything left of this line, lower fenestration and doors-to-wall ratio, that money is better spent on the insulation in terms of overall energy savings. But above that line, you actually save more energy and achieve higher comfort by going to the triple glazed window before you add the extra inch, the extra 2 inches, the extra 3 inches. Now, sometimes we get caught up a little bit as presenters saying, well, which one is best, right? And I'm going to change the language on that a little bit and say, what other considerations do I have to have here? There are other reasons to do continuous insulation on a house that might not be energy related. And so when we say, let's make a good window decision, we also have to keep in mind that it can't be at the expense of other relevant and important things that we're considering in our houses. That's called house as a system thinking. Understanding that every lever we pull in a house over here affects 6 other things over here that we have to now think about. And they all tie together. Yeah.
Just to add to that, one of the things you can't really quantify is comfort, like you said. So I'll give you an example. ICF house, R22 effective value on that wall assembly. Compare that to a effective wall of R22 with wood frame, uses the same energy. Which one's more comfortable? Right? Because the thermal stability of that wall with the ICF is so much higher. And you get the energy, or you get the ICF guys going, yeah, but it performs like an R40. No, it doesn't.
No.
It still uses the same energy, but the comfort level is so much higher when you put continuous insulation. So when you compare this chart, I think this is such a huge value added. Like this should just go ding in your brain and go, holy mackerel, this makes so much sense.
Yeah. One of my favorite sayings in our industry about energy modeling is that all energy models are wrong but some are useful. And that's to say you can't rely on your energy model to tell you the truth about what your house is going to be. That comes from other places. What the energy model can do is help us make informed decisions about total energy use and other things, but it's not the whole truth and nothing but the truth. It's just a piece of the puzzle. So let's talk a little bit as this house as a system thinking about the interplay between the solar heat gain of the windows you choose and the mechanical systems that you're putting in this house. So what we have here is the same chart, same 3 window U values across the top, same 2 choices for solar heat gain for each one. And below that you have the heat loss in BTU per hour and the heat gain in BTU per hour for the house across the board. Now, something you'll notice here is that for any given window, between the 2 solar heat gain choices, the heat loss number hardly moves at all. Because free heat from the sun has nothing to do with how fast the window loses heat through convection, conduction, and radiation. It's a different piece of the equation, right? So what moves the needle for heat loss is U value. As you improve the U value, you change the total amount of heat loss because you are losing less heat through the window. This is going to affect the size of your furnace, right? On the other hand, if you look at the solar heat gain impact on heat gain, which defines your cooling system, your AC or your air source heat pump, you'll see that actually if you compare the 0.4s to each other, it hardly moves the needle at all. But what does move the needle is going from a high or mid to a low solar heat gain coefficient dramatically changes the heat gain profile of the house. So you can start to associate those things in your mind. U value affects my furnace and solar heat gain affects my air conditioner in terms of sizing, right? So in all cases, going to a lower solar heat gain glass with this house that we're looking at today cuts the heat gain by about 1/3, which is pretty dramatic, right? 10,000 BTU, 9,000 BTU, that's nearly a ton of smaller cooling size required for this house. So as we make decisions early in our process of design to try and get to the optimal window, we're considering all of these things. So we may start by saying, okay, a U1.6 mid-gain window at 0.4 is achieving my energy goals. But what does that mean? It means that my demand for cooling is at 30,000 BTU. So let's make a decision now to go to a low solar heat gain glass, save a ton of cooling, and achieve a 20,650 BTU an hour cooling load. But what happens here? 1 ton of cooling load difference is great and has a monetary impact on the cost of that equipment. But we've also now moved the energy model and we have to account for that in some other means. What else happens when we do this? When we move from a 1.6 with a moderate solar heat gain to a better U value and a better or lower solar heat gain, you actually have an opportunity to save on the size of the ducts. So in this case, because we've improved both the U value and the solar heat gain value, we're moving the needle on both the heating load and the cooling load, stated here as design heat loss and design heat gain, moving them down. And this allows you to go from a 4-ton air source heat pump to a 2.5-ton air source heat pump. But maybe more interesting for those of you that might want to consider a finished basement rec room for your clients, going from a duct size plenum of 28 by 10 down to 24 by 8. Something smaller that gives you a couple extra inches of ceiling height to work with. So lots of ripple effects as we make these decisions. So let's talk a little bit for carbon emissions now. Now, carbon emissions are already a part of the 2025 National Building Code that's going to be coming to the provinces in about 2027. Operational carbon, just to talk through this, is the emissions related to operating the house. The people living in the house have to buy gas for their furnace, have to pay for electricity, and generating the electricity and burning the gas create emissions in the atmosphere. And there are some rules in the new national code to limit this. This is not really going to be dramatically different for us, because we've been using energy to effectively talk about carbon emissions as a proxy for about 15 years, maybe 40 years if we're really being honest, because all of our energy efficiency and housing work started with the oil crisis back in the 80s. But it's coming to codes as emissions. And what's going to come in the next code cycle in 2030 is the code is going to start looking at the emissions that are embodied in the materials that you use, that are produced while those materials are being harvested, manufactured and transported. How does that tie into windows and what we're talking about today? The operational carbon emissions of a house are directly tied to how much energy that house requires and what fuel source we are going to supply to meet those energy demands. So as a very rough example looking at this home, as we move to a better window with a lower U value and less heat loss, we actually see that the total annual operational carbon emissions, which are expressed in this very easy to remember metric of carbon dioxide equivalent per year tons. There won't be a test, as Darrell said, but that is the metric. You can see the numbers moving down from 4.6 down here to 1.22, 3.7. Now, like so many of these things, this is not the only thing that moves this number. If this house switched fuel sources or had a tighter airtightness value or had other means of conserving energy, those would also move this number down. So we're isolating windows for this example, right? But a lower U value window means less operational emissions over the lifespan of the home. And typically when we're calculating this today, we're talking about a 30-year lifespan. My hope is that we're building homes that are 100-year homes, not 30-year homes. So these results would only carry on even farther. Embodied carbon is different in so many ways because as a builder, you have direct impact over the embodied carbon emissions of your home by the materials that you specify and the materials that you select. And this is another area where we're learning that it's all about balance. Sometimes we have to add carbon into the home in order to save carbon over the lifetime of the home. One good example of that is exterior insulation. If you are building a 2x6 wall, and you have been for years, and all of a sudden you add 2 inches of foam to the exterior to save energy, that foam comes with an upfront embodied carbon cost. It means that there were emissions produced by the manufacturer to create that product for you to use on the home. Over the lifespan of the home, the question is, will that 2 inches of insulation save me more emissions than what it cost me to add it up in the first place? And the same is true when we look at windows, but on a much smaller scale. And this is something where we have, I would say, imperfect accounting right now, and it's going to change over the years. But if we look at frame material for the home in question, the embodied upfront carbon emissions of a vinyl window might be 4.7 tons. If we switch to a wood window, which is a better carbon material selection, that might drop by almost 20%, right? And wood might have other advantages related to hail or to fire that we talked about, but it might also cost twice as much. So how are we going to balance those things out? Now, some schools of thought would then ask the question about glazing, right? So we've saved carbon in the frame. That's a good news story. But it's not the only thing that defines energy performance. I think we know that now. Let's talk about glazing. We understand generally that going from 2 panes of glass to 3 panes of glass gives us more performance, or at least gives us the opportunity to push the performance even farther, right? But more glass means more material, means more upfront embodied carbon. So in this case, we go from a double glazed window at 4.7 to a triple glazed window, adding some upfront carbon out of the gates, about 0.7. That's working out to an almost maybe 15% addition in this case, if my math is not too wrong, right? This is where it gets nuanced. This is where what you don't want to hear and what you don't want to start saying is, well, if it adds carbon, we can't do it. Because we want to know what the payback is here. How much carbon emissions can we offset by adding this to the lifespan of the home? So if we put these two things together and we look at adding 0.7 tons of carbon up front the day the home is built and occupied, but saving 0.9 tons of carbon every year that that house is lived in, how long is the payback, if we're using a financial term, on carbon in this case? Well, it's less than a year, right? By year 1, you will have saved more carbon than it cost you to add that extra pane of glass into this window example. And then for the next 99 years, it's a good news story from there on out. So the really good news story here, the takeaway in general, if you're not familiar with the carbon accounting world yet, as it applies to buildings, is that if you're already starting to educate yourself about energy efficiency, carbon is a natural follow-on. And it's actually not the energy efficiency parts of the home that are going to matter so much in the embodied carbon space as decisions about things like concrete, masonry siding, possibly things like drywall and other materials that don't really play into energy efficiency directly. So don't conflate the two things. Question? Mike's coming.
I know this is a very complex question and you don't have a lot of time, so just simplify as much as you can. But operational carbon is really easy for an energy modeler to account for.
Yes.
Embodied carbon, would those calculations, is that going to be wrapped into the new code, and will that fall onto the builder's shoulders?
It's a great question. So embodied carbon in the 2030 code today, all that exists is the idea that it should be there. They have not started to explore how it's going to be calculated, who's going to do the calculation, what reporting is going to be done. But it can be done today by an energy advisor using the MCE2 tool, which I'll get to here. I don't know if I have a slide for it, but the MCE squared tool can take a HOT 2000 model as an input and give you your embodied carbon calculation for all of the assemblies that you have defined in that model, and give you a useful number you can share with the builder today. It's very likely, because that tool was developed by Natural Resources Canada, that what we see in the 2030 code will be very similar to that. But that's very much speculation. I can't make any promises there. The other thing that's changing, to dwell on that for a sec, is that we haven't been able to today to account for the entire house. Some categories are very easy, like materials, like wood and insulation are very easy to account for because it's one manufacturer reporting on that. But a furnace is very complicated to report on because the parts that go into a furnace come from so many different places all over the world that life cycle accounting is much more complex. So the tools that we use today are only reporting on 80% of what's in the house. Doesn't mean that they're not right. It just means that they're not complete. And it's a good, better, or not at best yet scenario in that respect. So this chart's just showing that payback. So if we look at the carbon emissions of windows, you've got 4 different colors here representing 4 different qualities of window. You can see that up front, the carbon spend is pretty similar across all 4 selections. But over time, the better insulated window, the 1.22 window, is saving a substantial amount of carbon compared to the higher U-value window over 30 years, something that we're going to see much more. So comfort, more comfort, better comfort, all of the comfort that we're promising to our homeowners. Let's dive into this a little bit. Of all of the things that we do with energy efficiency in mind, I would suggest that the right selection of windows is the biggest impact on comfort that you can make for your home buyers. You have to get the furnace right, obviously. You have to be able to keep the house at 21 degrees Celsius. But how many of you have sat in either a conference room like this or somebody's living room and the thermostat says 21 degrees on the wall and you're still cold, right? It's common. We've all experienced this, right? Or you look at even in your car and you've got the thermostat at 19 and you're boiling because the sun's coming through the window and cooking you. So comfort has to do very much with how our bodies deal with heat and lose heat to different surfaces. And we're going to look at that for a second. One thing to put out there is that we say that that comfort is hard to quantify. There is actually a standard for calculating and determining what is objectively comfortable. It's called ASHRAE 55. We're not going to spend a lot of time on it, but it does exist. And there are people out there who specialize in calculating and assessing the comfort criteria of rooms. So if you have a high profile project and you're very concerned about being accurate in your delivery of comfort, there are things that you can do to dive into that in more detail. But what comes out of the standard that's very interesting is an observation of where the human body transfers or loses heat. 15% of it has to do with the relationship of the humidity in the air and our amount of perspiration. 35% has to do with the movement of air. Is the air moving or still? Is it windy, breezy, or dead calm? But 50% of our comfort is derived by the radiative temperatures of the surfaces around us that our body can see. So even though I am very far from that window behind Darrell at the back of the room, my body can still see that window, and I'm actually, in real time, every second, losing heat to that window. And that's being counteracted by the mechanical system in this room providing heat to the air, which my body is trying to absorb to balance that out. But the radiative losses to the window happen more quickly than the other measures that contribute heat back into my body. So if that was a poor window, Joe and Darrell would be frozen back there. even though it's 21 degrees up at the front of the room.
Art?
Yes. Are you frozen? Is it a bad
Yeah,
window?
I'm freezing. Temperature up? I was just thinking, if you were standing there with a thermal imaging camera, right, that camera, when you point it back here, it's going to see the cold spots.
Yes.
And that's how fast you're transferring the heat, right? That infrared radiation from your body is being sucked into that window at that rate. So that's why you're feeling that so quickly, even at the front of the room.
I love that. Yeah, absolutely. Absolutely. So we actually did a little study on this internally at Building Knowledge. We used, actually it was my partner Andy and his wife were the example for this. We wanted to understand what really is the amount of comfort or discomfort related to a window decision. Could you quantify that in hours? So in this example, we looked at a scenario where the house is in zone 5, 6, so a little bit warmer than here, but think like southern Calgary. Somebody is sitting 1 meter from a glass patio door. This might be in a dining room, right, or something like that. And in order to be comfortable at that distance from that patio door, the room side glass temperature has to be at least 14 degrees in the winter, and in the summer, the hour on any day can't be greater than a heat gain rate of 70 BTU per hour per square foot per degree Fahrenheit. So don't dwell too much on those. The question is, what happens? We put in a single metal frame patio door. This might be an existing home that you're renovating, has this in there already. With that patio door, you're going to measure over 3,000 hours of winter discomfort and 300 hours of summer discomfort. And how many times is the phone going to ring from your client about that, right? We're not doing single metal frame windows, thankfully, so let's actually look at what we are doing. If we use a double pane with a U value of 1.4 to 1.6, with a solar heat gain of 0.55, so an off-the-shelf patio door vinyl product, we put that in. That same objective measure using ASHRAE 55 determines that we'd have over 500 hours of discomfort in the heating season and over 75 hours of discomfort in the cooling season. Who's worried about 75 hours of discomfort? How long is the heating season in Calgary? Or sorry, the cooling season. Let's say the cooling season to start, right? It's not that long. 3 months, really, where it's hot. Maybe stretch that to 5. Count that into days and then divide 75 hours into that and ask how many days of discomfort does that translate into? That's like 25 days out of 3 months. It's not good, right? What if we move up again? If we get to a triple glazed patio door with a U value of 1.2 or better, insulated with a low solar heat gain coefficient of 0.22, according to ASHRAE 55, discomfort in both seasons is now negligible at a distance of 1 meter. So these are not just people saying, yeah, I think I feel the difference. This is an objective way of calculating comfort, proving that we're not just kind of, spit and smoke up here. These are real things. Yes.
So you set a group of salespeople down and you explain this. Yes, you're going to save money on the operation. Yes, it's going to cost you a little bit more to put those windows in. But when you explain this, how do you go back later and phone the home builder and say, yeah, your windows are very uncomfortable? Well, we told you.
Right. And we don't want that. Even the idea, do you want to be telling your homeowners, look, you're going to see some condensation on your windows, but don't worry about it? Or do you want to be telling your home buyers, you're not going to see any condensation on your windows because we put such good windows in? Now, it's easy for me to say that when I'm not the one buying the windows, but it's a consideration that I want you to keep in mind. So unfortunately, I had to put a strike through on this slide because unfortunately, for whatever reason, Cardinal Glass had this fantastic visual representation of comfort in a room based on window specifications. It was awesome, and they took it down, and then they relaunched it only for US locations. And I don't know why they did that, and I wish they didn't. But we did do some screen grabs just to show you what was kind of an interesting takeaway. And if any of you hear the name Robert Bean and get a chance to see Robert Bean speak, he talks about comfort very much. And he often talks about actually losing the use of square footage in a house if that square footage is not comfortable. And this is an example of a living room where you've got a giant living room window, and based on the window that's going in here, a U1.8 and a high solar heat gain, this thermal calculator from Cardinal was showing that 2/3 of this room would be uncomfortable. You'd have back of the room comfort only. And if you always know that your room is uncomfortable in the winter, you might not put your furniture in that uncomfortable zone, and it might effectively make your living room less usable square footage, which is not ideal. Why build useless square footage? If you do the same model in this calculator with a 1.18 window and a low solar heat gain, we see that now you've got comfort near the window. In this location with this window size, you're going to be okay. And they had the same calculator available for summer conditions. So at a solar heat gain of 0.47, this would actually be uncomfortable. And this calculator was great because it included the surfaces and the coatings that were being used to determine this. So if you wanted to remember those specifics, you could. But going here to a 0.19 allows, with the blinds open, for this to be a comfortable room for the person standing in that space. Windows also interact very much with our interior air condition as humidity comes into play. And the way that you can reduce condensation on the interior of a window, a number of ways we talked about, you can either improve the condensation resistance of the glass and the window, you can introduce air movement to handle it, or you can lower the humidity of the interior air. Typically, we don't want to lower the humidity of the interior air too much because there are a number of reasons, right? What do homeowners want? Well, they want higher humidity. What do hardwood manufacturer warranties want? They want higher humidity, right? There's a lot of reasons for us not to drop humidity down to 20% in the winter, which would help our condensation issues quite a bit. But really, from a health perspective, ASHRAE recommends that the optimum zone for health is right between 40 to 60%. And that's where you get the least conducive environment for the buildup of bacteria, viruses, mites, respiratory infections, asthma, etc. There's a bit of a sweet spot. And the red line here is what ASHRAE recommends, which is just below the optimum zone for a winter design level of humidity to try and maintain an indoor air condition that is compatible with high performance windows so that we eliminate moisture on the windows themselves. Now, why do we care about moisture on the inside of windows? Is a little bit of condensation going to damage the glass or the vinyl frame of your window? Probably not, right? Vinyl is plastic, glass is glass. They can handle water, not a big deal. But where the problem comes is when we start to have that water run down off the frame onto the sill and possibly even down into the assembly of the window below or the wall below. And that's where we start to get long-term mold growth that we don't see until it's too late. So we want to really understand and manage that condensation as we can. And as we go forward, there is research ongoing that is informing the development of codes being done by the National Research Centre of Canada, saying that climate adaptation measures are going to become of greater and greater importance. That we're not just concerned now with slowing the rate of climate change, but because it's happening all around us all the time, we have to react to it and build homes that are going to be more resistant and more adaptive to the climate that we find ourselves in. And so there are a number of things going into that. Design temperatures are changing, moisture index and rain amounts are changing, and this will start to play into things that we're going to get into next with how you install your windows. How do you manage bulk water to make sure that you're not introducing problems by buying a great window and installing it in a suboptimal way and having the wall beneath it rot out 10 years down the road. So there are a lot of things being considered. We're going to spend some time before the end of the day on installation, which I think is one of the best takeaways from the session that you guys will have. And all of these things starts to matter in terms of climate adaptation in order to start to address terms that are going to be new, like passive survivability. Has anyone heard the term passive survivability as it relates to houses before? Okay, I'm not surprised. What passive survivability talks about really is if that building were to lose power, how long could you survive in that house? How slowly does it resist heat loss or heat gain so that the interior environment can support life before people have to evacuate and go to a place of safety? And this is not a code issue, right? This is so far beyond code. But this is something that in certain locations or in response to certain events like the heat dome in BC a number of years ago, that people are starting to look at what measures we can adapt. So when it comes to windows, low solar gain windows are going to heat up more slowly in the summer. Better U values will lose heat more slowly in the winter. But also doing things like properly designed overhangs that optimize shading and heat gain are going to contribute to the performance of these windows and the performance of houses over time. An example of that, this is showing two buildings, building 1 and building 2, in a summer condition and a winter condition. And building 1 uses high performance envelope and window components, and building 2 uses code minimum envelope and window components. And in the winter, you can see that after 36 hours, building 1 has managed to maintain a 10-degree interior temperature, whereas building 2 is now at -8. Which one of those is more survivable, right? After 36 hours in the summer, the better built building is only at 30 degrees interior temperature, which is hot, but maybe not deadly yet. Whereas the other building at code minimum is at 41 degrees Celsius interior temperature. You're not able to stay in a house like that. So all of these things that we're doing for energy efficiency, for operational carbon, et cetera, they're also helping us improve on other measures like this. But there's always opportunities to go farther, just to make you aware of what's out there. So the wrap up for this part of the session, window selection, is it simple or is it complicated? It's complicated, right? It's not something that I don't think anyone in this room is expected to walk away and be able to do all 3, 4 of these presentations back to back, because there's just too much to know, right? And the good news is you don't have to know all of it. You have to know the people that do. You have to know the suppliers that understand the products that they're representing so they can give you answers about solar heat gain, about U value. You have to know energy advisors who know how to optimize your window selection for the house that you want to build and what's available in your locale and how you like to build. You have to know trades that know how to install the windows that you select. And we're going to talk more about that at the end of the day. And all of that plays into your determination matrix here, which I think is a part of the handout that I encourage you to come and pick up at the build stand after the session is over. And with that, we're going to take our second 5-minute coffee break. This one, a true 5 minutes. We'll get switched back up, and Darrell's going to come up and talk about the installation of windows, which I think is probably the hottest topic in codes these days.